Good morning, everybody, and welcome once again to the JKMRC Friday Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and the custodians of the land on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to the Australian and global society. It's my great pleasure to welcome Dr. John Bishop here today. John is a geophysicist with nearly 50 years of experience in the natural resource industries. He has founded and co-founded several public and private resource and energy companies, including Kooth Energy, which discovered and defined geothermal resources in Australia and the Southwestern Pacific, Direct Lithium, which has a large combined geothermal energy plus metals license in Tasmania, and Spark Energy, which with geothermal assets in New South Wales. He's also the chair of MITRE Geophysics, which serves the Australian and international mining, energy, and engineering industries. So the title of his talk today will be Lithium Extraction with Geothermal and Oilfield Brines. Please join me in welcoming John.
Thanks, Kristy. Ready to go?
Yes, you're ready to go. Thanks, John.
Thank you. Okay, I was asked to keep the title short, so I left off direct, but direct lithium extraction is the more complete title and the subject of the talk. The usual disclaimer and short bio by Kristy, thank you. And getting straight into lithium. Lithium gives you the biggest bang for your energy buck and will continue to be important for storage applications, particularly mobile applications, electric vehicles, and that's where most of the demand is forecast to come from. You can see from that image in the top right that we're in 2024, we're just on the cusp of this exponential increase in demand, forecast increase, and it's by no means certain where that gap is, how that gap is going to be filled. And I'm going to show, I hope, that oil fields and geothermal brines generally, if processed by DLE, will help help reduce that supply-demand gap. It's still an immature industry, and the price volatility has been high. See that large jump in price in 22, followed by an equally fast fall. But in 2024, the price is still higher than it was in 2021. So we'll talk a little bit more on price. I've got a whole lot of small print in the bottom left, which is not for going through now, but it's a number of facts and notes that I found useful when trying to learn more about the lithium industry, the lithium market, and so that's for later reading. Going to lithium resources, most of the world's resource is this is the current resource. There's a lot happening in lithium, but if you go into the literature and look up resources, you'll find that most of it's in these unconfined, shallow salar aquifers, lakes. Most of that is in South America, with a fair bit in China, and the next resource is in hard rock, mostly in Australia, but increasingly Brazil and Canada. Then there's some sedimentaries and clays, and then lastly, about 6% combined resource in oilfield and geothermal brines. That's not reflected in the current supply. Most of it's coming from hard rock. Most of that's from Australia, produce a concentrate of about 5% lithium oxide, That goes off mostly to China for processing, and that's the current dominant supply. About 30% comes from evaporation of salars pumped to the surface, add reagents for a sequence of precipitation of contaminants, and you end up with a dirty lithium salt, and that too goes to for further processing. But about 10% of current lithium supply comes from direct lithium extraction process on salars. There's no current commercial. We're on oil fields and geothermal are on the cusp of commercial production, but at the moment there's 10% that comes from salars. And just looking a little bit more at brines and DLE, this diagram comes from Alex Grant of Jade Code Partners. If you want to know more about DLE, Jade Code is a good place to start. And there's the website down there in on the bottom. But so you can see the salars, we have current production, low temperature, low pressure, increasing temperature pressure through oil field, and then geothermal, a large range of pressures and temperature. And then if you look at the pH, the oxide potential there, they're pretty much reversed. It's important to note that the oil field and geothermal brines can currently really only be processed by DLE, and salars will be increasingly treated by DLE. In the previous slide here, I had the point that Chile has the stated policy of no more new mines with evaporation. They should all use DLE, and that's a policy that they're trying to stick with. Looking here's the main image. There is shows the current DLE projects and operations. Over here in China, these are DLE purely. Some of these here in South America are DLE, some DLE plus evaporation, a hybrid, and others are projects. We've got a whole range of projects, oil field projects in North America, and then a large scattering of geothermal projects. Bottom left image shows the grade of these brines. Most geothermal plays are low in lithium, but those that are high are generally around the 200. Now, this is correctly, it's milligrams per litre. It's roughly very close to equivalent to parts per million, ppm. The difference is in the density of the brine, which is generally not significant. I'm going to probably say ppm most of the time because it's quicker, but the actual grades in milligrams. But you can see here that there's quite low. This is 75 ppm from Alberta, and then an even lower one in a salar. But these, the financial documents suggest that they're really potentially quite profitable. Going in a little bit deeper, what is DLE? DLE's describes, it's a term, to describe a toolbox of a set of standard chemical and physical processes that can extract lithium from solution. Adsorption's been used commercially for 25 years. It started some 50 years ago, and the other ones can be regarded, depending on whether you're a proponent of them or not, but if you don't mind, then these are perhaps R&D processes for unusual brines, and also for looking for different ways of making the whole process more effective, higher recovery, better grade, etc. So this is an example again from Jade Cove, taking a typical geothermal brine. He's used 200 milligrams of lithium in the brine, and then 2,000 of magnesium, 30,000 calcium, 500 sulfates, a typical brine. That all gets re-injected back in, except there's a 10 to 100-fold increase in lithium that goes into chemical plant for refining. And at the moment comes up either as the high-end batteries use hydroxide or carbonate, and that may change. I read about solid-state lithium batteries being the way to go. And then there's a little bit more detail there on the different types of absorbents, etc. So what are the pros and cons of DLE? So the image here has got DLE in green, and then solar evaporation in blue, and hard rock mining and processing in brown. This is the recovery. You're getting well over 90%, 95%, one company 96%, and seems to be continually improving. And you're getting about half that in solars and maybe 60%. So one way of getting a larger supply is to go to DLE, particularly for solars, and you'll get a whole lot more lithium. The water usage, if you do it correctly and reuse it, very little water usage for DLE. As I alluded to before, the problem with the evaporation in the South American deserts, not only is it losing water to evaporation, but it's also upsetting, in some cases, the freshwater aquifers that lie on top of the salt waters. You interrupt the salt water beneath, you're going to affect the freshwater ground table. That's a problem. Then lastly, the CO2 emissions are effectively zero, and they can be zero if you're using, for example, a geothermal power plant. And we're going to look at Vulcan Energy in the Upper Rhine, and they've registered the name Zero Carbon Lithium. And then lastly, you may not even be able to see the little green dot that's at the foot of the footprint, which is DLE's footprint. In short, it's a sustainable, low impact way of producing lithium, and I think it's the way to go. So why isn't everybody doing it? One of the main reasons would appear to be that each brine is different, and the process that's needed to optimize the lithium extraction requires a whole lot of tweaking, and clearly this has been taking of the order of a year or so with these pioneers in brines, and the process will rapidly improve as people will start on the back of others' experience. But there's quite a bit of secrecy still in proprietary processes, etc. May have higher costs. Certainly, it does have a higher capex than evaporation, but need to make sure that we compare like with like, that we're talking about the end products, and you add in all of the costs. It may, in fact, not. There are a number of companies saying that this is the cheapest way to do it. The other point from an investor's point of view is it's a rare investor that wants to be at the leading edge. Many say that I'm happy to be at the leading edge, but that still means they want other people to have done it first. So despite the fact that 10% of the world's lithium is coming from DLE, there's still a bit of investor skepticism. One of the other, I don't know whether it's a con, but it's a factor that needs to be mentioned, and certainly I've been asked this a few times, is what about dilution? If you, and remember, you've got a production hole and in simple terms, one production hole one reinjection hole. If you put them very close together, then you will very soon be getting your own back, which will be a lithium-free brine. So this is Alex Grant, again, Jadeco's, I call it the Goldilocks diagram. You've got here, if you put the injection hole too close, you're going to get rapid dilution. If you put it too far away, then, and you do have to put it back into the same reservoir. If you inject into another reservoir, you're going to reduce the pressure of your resource. That means more pumping, and you're going to find it harder to pump into the separate resource. You'll be getting higher pressure. So you've got to find that right mix. And this is the bottom right is a diagram from Vulcan Energy, which shows they've got their production holes along the high grade fractures, but they re-inject as far away in the somewhat lower grade parts of the aquifer. And they've done some modelling, and they've got here a 1.6% dilution, starting at 180 ppm. After 30 years, they're down to 110 or so. That's in their modelling. Take them 10 years to see how accurate it's going to be, but it's factored into their financial modelling. So we'll have a look at some case histories. We look at Alberta oil fields, the Smackover in southern states, Cornwall, UK, Upper Rhine Grub, and then lastly, a project dear to me here in Tasmania. And we'll look at the geology and the resource, the DLE process, and financial estimates. But it's not going to be a deep look for any of them. It's going to be an overview. Starting here in Alberta, up in the northwest, Rainbow Lake, which is still, as I read it, is still an active oil field. And looking at this schematic, we've got an emulsion of oil and brine coming out. The oil gets separated, sold off, and I think that's a separate entity, company. Take it to the brine, give it a brine treatment, which removes apparently 99% of the contaminants, and then a proprietary DLE system giving them a saleable lithium. So the beauty about these oil field brines is that they invariably got a large amount of data, a huge database. Here we've got 1,300 existing wells. It's 2Ks, and so that you automatically start with a resource. And I'm intrigued as to what the resources, particularly with geothermal, which I know a little bit more about. Say most of the geothermal resources plays are low in lithium. I can't tell you about the distribution of lithium in oil fields, but the source in Rainbow Lake is an enrichment of seawater in the unconsolidated sediments with some hydrothermal enrichment. So they've got an average grade of 50 ppm lithium, but it's quite a reasonable range. It's a range, I think, from about 20 to 120 across the resource, which is 4 million tonnes of lithium carbonate equivalent. You've got to divide by 5.232 to get the amount of lithium. So it's about 0.8 million tonnes lithium metal. Starting at 1,000 tonnes per annum, expanding up to this 23,000 tonnes is a more typical output for the projects. See, it's not clear to me whether it's, and maybe it isn't clear to them, whether they're going to produce a lithium hydroxide, or this actually should be lithium carbonate. Quite often it's lithium carbonate equivalent for pricing. It usually is carbonate equivalent for pricing. This price, so it said, at the moment we're under 15,000, and they've used 25,000 for their modelling, but 25,000 from my research, listening to podcasts, etc., 25,000's the number that many think is required to generate. It's an incentive price that incentivizes people to start new projects. If you're down at the current 15,000, existing projects will make money, maybe new ones, but there's not that gee whiz factor that said we should get into this. And that we need that extra supply, and many people think that 25,000 is going to be the sort of price that it will sit at to match, so that supply matches demand. The OPEX is around the $3,000 a tonne of LCE, and there's a CapEx of $1.5 billion, and supposedly starting up next year, and the lowest project that I've come across that seems to be relatively advanced. So, been staying in Alberta, but going down to just near Calgary is E3 lithium. This is 75 ppm lithium, and it seems to be a much more uniform resource. The various places where they assayed for the lithium, this is quite a large holding that they've got in this area of Alberta. It all appears to be around the 75 milligrams of lithium. Their Goldilocks distance between injection and production is 15 kilometres. So everything will go down to this processing facility and then get re-injected over around about the 15 kilometres. They're planning 20,000, so typical tonnes per annum of lithium hydroxide in their case, although they're talking about also going to an 7 to 8 times factor for that, with starting construction in 26. So we don't have I haven't seen a start date, a proprietary sorbent process of the DLE, but getting over 90% of battery projects. Their modelling price of 14,000 is what it is now. That price, the study was done at least a year ago, maybe closer to 2 years ago. So the price they're used matches current price. They've got a 3,500 OPEX, and this looks like a very promising project. Certainly, Alec Grant, who I've referred to before, has said that it's done a lot of work, looks good. It should happen. So staying in North America, but going down to the Smackover formation. This is a large, this inset up here shows it going from Texas to Florida, and all of these black dots are the existing oil field wells. And if we go into here for the main diagram, see we've got a number of players. The Exxon is the big boy in the band, and we've got Pantera Minerals being able to claim neurology next to Exxon. Albemarle's one of the major, if not the major, lithium producer in the world. Standard Lithium has got these two projects. It's also got more land over in Texas. Land licensing and permitting, that's one advantage Australia's got over the States, where the licenses are held by the landowner, although not necessarily. It seems that you can sell the land, you can sell the rights to the minerals, and oil's another thing separately again. So you've got a landowner, you may have someone with the oil rights and someone else with the metal rights. It can be minefield. But we'll take Smackover's Southwest Arkansas project, SWA. They're down at about 3,000 metres. They've got a good grade here. We've got 400, so it's 10 times that of Vulcan lithiums in northwest Alberta. But small resource, but that will grow. There's not going to be a shortage of lithium-rich aquifers. 30,000, so it's really quite big, starting in 26. Large caution there for processing. And I've just put this out here because it's a number of different processes. So it starts with filtration, then it goes to absorption with the barren brine re-injected. Then the eluate, the lithium fluoride dirty solution, goes for ion exchange for further purification. Not sure what the RO system is, and then you end up with a lithium fluoride salt. Similar OPEX and the current price or their modelling price assumption of 30,000. Maybe that's a little bit optimistic, but pardon me, but it shouldn't be too much out of the ballpark. But so this isn't the only part that's prospective. There's quite a lot of other about to happen, I suggest, in the Smackover. Going now to England, here's or to the UK, I should say. Here's a map of the heat flow. We're now talking geothermal brines, and which require heat. So here's the heat flow, and there's some action up here in Yorkshire with the Weardale granite, which is an interesting granite for its high porosity. There's a couple of papers and they talk about why and how it's got such high porosity. Don't have any lithium values from it, not from memory anyway, but there are at least a couple of projects that have started. There's some land holdings. Land holdings can be even more tricky in the UK, where the ancient duchies or aristocratic land holdings, they've been broken up, but the mineral rights have stayed with the original holding. So it can be tricky. But the advanced projects are down here in Cornwall, and I've been looking at this one for quite a long time. It's the United Downs Geothermal Engineering Limited, GEL, is a private company, and they've got a geothermal project, a power plant project, and that's what they want to do, and that's what they're about. And there's also, they've got a neighbour, Cornish Lithium, that's into lithium, and I think they've tried to see if they could have an association, work jointly, one with the power and one with the lithium. But Cornish Lithium's certainly doing things on its own with some clays. Interesting, it's kaolinite used for china making long time ago. This is the weathered part of the granite. Perhaps I've jumped a bit into saying that the source of the heat in Cornwall, the source of the mineralisation, the tin mines, etc., that go back some thousands of years of mining history in Cornwall, are due to high heat producing granites, and they contain a decent amount of lithium. And in fact, lithium was isolated from the brines there back in the 19th century. So the lithium content's been known for a long time, but it hasn't been that exciting until recently. The GEL have got a value of 250 milligrams per lithium at the bottom of their deep production hole. and this, you'll read quite a bit about we're getting values to such and such, but the overall resource is invariably lower, and I suggest it's likely to be around the 200. Cornish Lithium's strategy, again, it's another private company, so there's not that much information. They are going for shallow holes. They're getting a lower grade, which they're not, they weren't until they haven't released what that grade was, but it's hot enough for district heating, and the grade's high enough to go into a DLE plant. So they're saying we can do cheaper holes, quicker holes, don't need to worry about power, and the viable project that way. And that's what they're doing. So it's still geothermal, but it's not geothermal power, which is my main passion, is that we should be tapping the heat. I won't get distracted. Start talking about geothermal power in a lithium talk. This is the kit for this system is being placed at the moment, and it remains to be seen just how someone will take the rights to this lithium and extract it. 200 with all the extraction and injection in place. It's an obvious project to get going. Okay, going across the channel to Central Europe, we've got the Upper Rhine Graben, which is here at the intersection of Switzerland, Germany, and France. There's a number of working geothermal plants here, and they're tabulated. So here's the names, temperatures, the flow rates. Flow rate's an important factor. Important factor for both power and for volume of brine that you're going to produce. So here's the lithium grade. Again, these are around the 200 mark, and this is the amount of power. They're producing from half a megawatt to 5 megawatts. Bruchel is actually it's a low flow and it's a low temperature. It's quite high lithium, and it's the chosen site for EnBW, which is one of the big four, probably Australia's big four banks. Here's one of the big four utilities, and it's using Bruchel as a test bed for looking to see what are the options for DLE processing. We're going to have a closer look at Vulcan. Vulcan's ASX listed, so it's quite a lot of information about here. This is the Upper Rhine Graben temperature at 3 kilometres, and all these grey dots are Vulcan's licenses, not all exploration, some are development licenses, and they've got some working geothermal plants that they've acquired and that now need to be modified so that they can also extract the lithium. So they've got it's over 150 degrees at 3 kilometres. If we just go back, look at the cross section, we can see that it salts to go down to 5 kilometres. So it's got a granitic basin with a sedimentary basement with a sedimentary basin top of it. We've got, and if you look back to the table, we've got resources within the granites and within the sediments, particularly this sandstone layer right close to next to the granite. Going back to this diagram, look at the metrics for Vulcan. They've got a large resource, the largest resource in Europe, they claim, and I'm sure it's true, at a healthy 175. Planned production of 25,000 tonnes per annum. Starting in 2026, they've had a demonstration plant for some time. It's done some tens of thousands of hours, I think. An in-house absorption process, you'll see ADLE in their literature, and an OPEX of, at the moment, the dollar and the euro, US dollar and euro are pretty much 1-to-1. So this is a typical OPEX, and that's a typical CAPEX. But they do have a head start with a number of existing operations. This is to me, an interesting diagram. It shows that nearly 90% of their revenue is going to come from the lithium, with less than 10% from the power. And Germany gives a really nice feed-in tariff for geothermal power. So no one else is going to do any better in a power to lithium revenue ratio than Vulcan. So you really do need the lithium as the sweetener to get the geothermal up and running. Although, having said that, there's enough happening in the geothermal space, particularly in the States, where there are large, as in 400 megawatt geothermal power plants being built, and I've not seen any mention of lithium in them, and it's highly likely that there's very little lithium. Okay, if we could go and start with a project that's dear to my heart, which is Lamont in Tasmania. This image shows the energy and mining infrastructure in Tasmania. It shows why Tasmania is a tier 1 jurisdiction for energy and mining. It's self-sufficient in hydro electricity, but there's increasing wind being built, and there's even solar here and up here, and wind here and wind along the west coast. But Tasmania's got the stated policy of wanting to be the renewable energy battery of the nation, which requires a rough doubling of their, I think it's about 3.5 gigs of total capacity at the moment. And there's no more dams to be built. So having some more dispatchable, scheduled, synchronous electricity from geothermal is going to be a good thing. But so here's the license, the granted license, the Lamont geolithium license, which includes an inferred geothermal resource. This was done by Vulcan Energy, which I co-founded way back. This was part of the big focus on geothermal from 2003 to 2013, roughly. The point about this is a conceptual play that's with no surface indications at all. There's little hints of geothermal, fossilized geothermal plays, etc. But there's no actual evidence of any geothermal activity in this area. There's a warm spring up here, and there's another one down in the south. But so why? What's the proof of what we've got? Here's the heat flow survey that Keith did, and the dotted line is the paleo plate boundary. That plays an important part. The tectonics and the structure play an important part of the story. Heat flow measurements, some of the highest measurements in Australia were recorded here. This is a legacy measurement, and this is a Keith measurement, both both anomalously high. So that covers the heat aspect. Then if we look at the permeability, and remember I'm a geophysicist, in fact, and Roger Lewis was the other co-founder of Keith with me, another geophysicist. Roger had done his PhD in magnetotellurics. We've used magnetotellurics extensively. These are all the stations in triangles, and we're saying that the resistivity is a good proxy for permeability. So we want high flow rates, we need high permeability, and we've got a naturally fractured play, and it's a fracture permeability, not a formational permeability, although that's not excluded. Low resistivities here, we're saying these are related to faults or associated with faults. we're saying that's high permeability. Can have low resistivities from other causes. Graphite, unlikely in a granite, but possible. Sulfide, certainly, that can be within the granite. But if we've also done passive seismic survey, if you get a low seismic survey coinciding with your low resistivity, then that's a pretty good, gives you significantly high confidence that your cause is a brine. We've got here this is the 5 ohm meter ISO surface, which is the sort of number that Keith used for its naturally fractured geothermal play. Wouldn't need any stimulation for zones less than 5 ohm meters. The surface, intersecting surface, is the interpreted depth to the granite, and so we're saying we've got plenty of permeability. What about lithium? The northeast of Tasmania has got a number of 3 batholiths, a number of plutons within each batholith, and here we've got the global average for granite is 30 ppm, and we've got rock chip sampling up to 9,000, over 9,000 within these are the granites. This outcropping granite here, the Ben Lomond batholith, which is the home of a lot of Tasmania's tin and tungsten mining, the Royal George, Aberfoyle, Storage Creek, etc. Highly anomalous in lithium, and more bands of fractionated granites, mineralized granites in the northeast. And we're saying that we know we've got hot granites across the license at depths from outcrop to 9 kilometres, and that coloured image at the bottom is the interpreted depths to the granite. So they're useful depths for getting high temperatures, and we're saying that they're fractured and that they're lithium-bearing granites. So that's all. And the other point that's covered is size. This is about 80 kilometres from north to south across the granted licence. So we've got a schematic geology of a hot lithium-bearing granite at depth that's intruded into the Ordovician, the thinner metasediments, and then later in turn been covered by the Tasmania basin with the upper and lower Parmena, and then a series of Jurassic dolerite sills, and which are commonly exposed. And there's a cross-section of the resistivity from the magnetotellurics and a proposed hole to test and confirm that that's what we've got. So, well, what might that mean?
Sorry, John. Sorry to interrupt you. You asked me for a 15-minute call.
Right.
So
Thank
just
you.
want to remind you.
Yeah, good. Thank you. I'll line it up for questions. So if we just take the 5 ohm meter isosurface and we just take that portion beneath the granite, we know that there's from holes that have intersected the granite, some of the mining holes, we get 2,000 ppm lithium in the metasediments. But this is the back of the envelope thing. How big might it be? We've got 150 kilometres of less than 5 ohm meters in the granite, and if we give it a 150 ppm lithium in the brine, then we end up with a very healthy 10 million tonnes of LCE. So that's, I think, that's assuming a 10% porosity of the 5 ohm meter surface. I think that's all fairly conservative, so it's an exciting number. Is the upside. So the strategy is we now need to drill a deep slimline hole up to 3 kilometres to get the metrics, get the flow rate, the temperature, etc., and prove the concept. Then this will be done with a slimline hole ending in HQ. And if that's all successful, we would then drill a second slimline hole, and we could probably generate, I'm told, up to 0.3 to 0.4 megs of power geothermally with a modular system, a series of containers. And we could also then put a DLE plant in, a pilot DLE, and work on the DLE. It would be a relatively quick and cheap way to demonstrate the viability of the project. And then last slide is this is the nomogram showing flow rate versus temperature. Normally I should have, actually, Australia's previous geothermal was all in this area, high temperatures, but no decent flow rates. And here's a series of geothermal projects. This is the Cornish one. This is Bruchel in the Upper Rhine, Vulcan in the Upper Rhine. And I haven't talked about Salton Sea, but that's a number of players there in the Salton Sea. Very high temperatures, very high TDS, and high flow rates. But there's not a great range in the lithium grade. And we're expecting something similar to that, and we're also hoping to have be somewhere in this zone for the month. That's it. Thank you very much.
Thank you very much, John. It was very interesting. It's good to see that there's a lot happening in this space, and I think especially that slide you showed at the beginning with the where you compared the water usage and the carbon footprint, and that I think there should be even more going towards this space. Do you actually think that there's enough adoption happening? Obviously, you've gone through all the new projects and so, but do you think that this should be adopted more quickly even?
I think it's going to be an accelerating change, Kristy. I think the advantages will become very clear, and the fact that Chile is saying no more evaporation, you've got to go for DLE, that's going to make a big change. There's a whole lot of resource in Bolivia that's not being mined at all yet. They've still got to sort out their nationalisation and ownership and et cetera, et cetera. But there's so many, if you go back to that, there's so many projects, and this is not all of them by any means. And I started, say, 3 or 4 months ago, and I keep adding them all the time. You know, I've added lithium here, I've added Volt here, I've added these northern, the Weardale ones that come in after them. So and they're all working on it. There's now, to my knowledge, two companies working on DLE in Melbourne, and there may well be more. There's a DLE conference, DLE only conference next month in the UK. So I think it's snowballing. Having said that, that sudden drop in price really scared the investors, and they dismissed it. But the demand for electric vehicles is still very positive, so the demand's going to be there.
Yes, thank you very much, John. We have a few questions from the audience here, so unfortunately won't be able to see them. But yeah, here's some questions.
Thanks very much, John. My question is, are there any byproducts or potential penalty elements, I guess, associated with direct lithium extraction from the geothermal wells? And I'm thinking, potential for rare earths coming out of the granites or uranium or things that either are potentially hazardous or potentially valuable or both associated with it.
Yeah, there's certainly some work going on in what other elements might be. It's such a good, sustainable way to produce metals. There has in the past, in the 19th century, boron was extracted from geothermal brines in Italy, and zinc, and I think magnesium being separated, extracted in the Salton Sea. I thought that uranium might be extractable, and might be. And if it's a penalty, then you just put it back where it came from, and don't say anything about it if you like. Don't extract it. But I was surprised at how low the uranium values are, where I've been able to get whole rock analyses, sorry, not whole rock, whole brine analyses of whole chemistry analyses of brines. They've been, particularly of the granite sourced ones, they've been surprisingly low in uranium. Now, I don't know whether that's, I'm not a chemist, I don't know whether that's temperature and or pressure, but the uranium values I've seen have been in 20 ppm, that sort of number. Because there were 2 points of view. One is, well, if you're going to have bringing up uranium, you're going to have a problem. To which I would say, well, we're going to put it all back. We're only going to extract the lithium. Or you say, well, is there economic uranium? But it would appear that that's not the case. Potassium is certainly being looked at, and I didn't mention, but meant to, that in the Smackover they've been taking bromine out of that Smackover formation for since the 1970s, for 50 odd years. So it was no great jump to suddenly start taking lithium out. So, and you would think that rare earths would be another hot contender, since it's a low impact way to do it.
All right, thank you, John. And there is some questions online. So Eric, do you want to unmute yourself and ask the question?
Yeah, John, I really enjoyed that talk. Apologies for not catching this. Do the oilfield DLE projects require any continuing production of hydrocarbons, or are they just using the oilfield knowledge and infrastructure but can be operated independently?
Yeah, when I first came across it, it was the description was depleted oil fields. So it was oil fields that were no longer being used, but they still contained the brine in them, and they had the infrastructure. But as I poorly understand it, the Vault, the Rainbow Lake in Alberta, is an operating field. And I guess you do have the potential for interfering with each other. So if it's not an integrated operation with the one company doing everything, but as I understand it, you can have both. I think most of the ones that are operating at the moment are depleted and not operating, but Vault may well be the exception, and it's an operating oil field.
Thank you.
There's a few other questions. Stephen, do you want to ask your question?
Sure. Thanks, John. Great talk. Really interesting. Sorry, I may have misunderstood something, but so please correct me if I'm wrong. I noticed on his first slide that the predicted demand by 2040 has about a 4 million ton supply gap. And a lot of the projects you've been highlighting can produce something like 25,000 tons per annum. So that kind of suggests we only need 200 of these projects to come online to be able to meet that demand. So what's your views on whether there's a risk that the market could kind of get saturated and the prices really remain low over time?
Yes, yeah, no, I think you're absolutely right. I should have done the maths there to see how many projects at 20,000 tons, how many it's going to take. It's not going to take that many. I think the persuasiveness of the DLE process will, particularly one of the companies, we started doing this and we're now got an 80% reduction in costs in our pilot plant because we've improved it so much. You would think that the DLE process is going to take over, but you're right. If you keep there's a lot of pegging going on in South America. use the DLE and get 90% of the lithium. Presumably there will be a balance of supply and demand, like there is for most metals, all metals, with fluctuations, and there's so that there's no longer an incentive needed. You just need to match your costs with a little bit of margin, and that will be about the 15,000. Now that's going to knock out a lot of, apparently that sudden rush in price was zinwaldite projects coming online in China and I think Africa, and they were low grade and difficult to process, and they don't work at anything under about 25,000. So you'll get that, they'll go out of the equation, and DLE will be happy to operate until it gets below, say, 15,000. But so that balance will be reached. And there is the other aspect, which is not yet important, but there's quite a lot of work going on. You can use DLE for recycling, and there's not a lot of recycling yet, of course. Batteries aren't old enough, but there's people already thinking about it, and DLE can be used for that. So there'll be a large proportion of the supply eventually will come from old batteries.
Yeah, great. Thanks, John. It certainly sounds like DLE is a very environmentally friendly solution.
Yeah.
Cheers.
Right. So maybe we have time for a last question. So there's similar questions from James and Tuan. So John, why is the carbon footprint of brine treatment so high compared to hard rocks or other types of methods?
That's the salars. This is such a high footprint because of the different evaporative ponds that are required for the process. So there's different reagents are added at different stages, and the whole thing just takes an awful lot of space. Whereas the DLE in the top, the factory in the top part of the slide is a series of containers going through these absorption processes where the lithium ions get absorbed onto the substrate and then get washed off. And you still need a lot of them because you're getting, each well will be producing from 50 to 100 litres a second. That's a large throughput, but it's all contained in one small factory. I hope that answers the question. I hope I've addressed the question.
Thank you very much, John. Unfortunately, we've run out of time, and there are still a few questions online, but guys, please feel free to reach out to John and then ask your questions directly.
Yeah, I'm happy to do that. I don't have my email on the slides, but perhaps I'll put it onto that deck that you'll put on the server somewhere, Kristy.
Okay, yeah, that would be good. Thanks. So yeah, thank you very much again, John. Let's thank him again for his talk. So next week we have Tom Patterson from Carbo Services talking about mineral endowment, known unknowns, and decision making in a highly uncertain business. Hope to see you all there. Thank you very much, and thanks again, John.
Thanks, Kristy. Thanks, people. Bye.